All right, so we're going to start the. This is the first lecture in the. This is almost external to the thermodynamics section, uh, but it's crucially important. It may be one of the most important and most relevant to your following careers after school um, topics. This could be the most relevant topic you learn in this class. Hopefully you've already learned it, and this is basically a review for the most part, right? And you should be this is a topic that should get reiterated in many of your classes, okay? Um, because of how important it is, and how important it is to understand that we're not just dealing with numerical quantities. These quantities have uh, magnitude associated with them, and the magnitudes, are crucially embedded, crucially tied in with the units that you're using. And so it's always going to be crucial that you understand what units you're communicating in. Okay. And for that purpose, units are always going to be a very large portion of, not a very large portion, but units are going to count. If you just put a numerical value as your answer on an exam, um, you're going to lose significant credit. Okay. Um, so it's always crucial that you understand what units you're working in, and you need to be able to communicate what units you're dealing with at all times. In this class, we're only going to be using SI units. Okay. So the base SI units are as follows. For a given dimension, which would be something like length, uh, mass, time, and then there's two types of temperatures. There's an absolute temperature, and what I'm calling here is a ordinary temperature. Okay, so absolute temperature given by capital T, and then an ordinary temperature also given by capital T. And so um, the SI unit for length is meters. SI unit for mass is kilogram. SI unit for time is seconds. And then temperature, absolute temperature is given in Kelvin. And then what's ordinary temperature is in degrees C. Okay. Many of these should be familiar to you. Okay, but these are the base units. And from these units, we can derive other more commonly used units. Okay, so there are more base units in the SI system. Okay, there's things like current and luminosity and things like that, but for our purposes, this should be enough to suffice. Okay, maybe with maybe we can add electric current. We're going to touch on this a little bit. And that has units of amps. Okay. And then we can from these quantities we can derive derived other units. Okay. And So derived units are basically just combinations of the base units, all right? So there's a derived unit for force, and its unit is newtons. And then in base units, that'd be a unit of mass times unit of length divided by units of time squared. Okay, so this is just another way of writing something like that. All right, so it's just multiplying with the use of negative powers, um, denoting that it's a in the denominator. Okay, there's also the unit of pressure, and its unit is pascals. And in base units, that would be force per unit area, or just like we wrote up here, you just divide this by meters squared. You get kilograms divided by meters divided by seconds squared. Okay. Then there's energy, and it has units of joules, and joules are given by or can be decomposed into base units in that way. So I've got kilograms times meters squared divided by seconds squared. And then power, which is just joules per second or watts. And so just divide joules by seconds and you get okay. And so what I find is an easy mnemonic for maybe mnemonic or method for remembering this sort of thing is I remember certain famous equations. Okay, and so there's Newton's second law is a good one. Newton's second law. And then if this is true, we're going to get into this in a little more detail in a second, then the units have to work out. So I have units of force. Another way of writing that is so units of force would be written with these square brackets. Has got to be equal to units of mass times units of acceleration. Okay, so units of force, we've given the label N for Newton. All right, and that equals units of mass, which is kilogram in the SI system, and units of acceleration, meters per second squared, which is exactly what I told you up here. So this is useful, you know what I mean? Because this is something that's easy to remember, and then from that you can quickly derive, you know, how, what exactly are the units of force in base units. That way you don't have to memorize all this stuff. Likewise, there's, uh, Einstein's famous equation equals mc squared, which, I could write out as the units of energy have got to be equal to the units of mass times the units of speed, or the units of c, which is speed, squared. All right, so the units of energy are joules, and that's got to be equal to kilograms times the units of speed are meters per second squared, which is exactly what I got here. Meters squared divided by seconds squared. Meters per second squared. All right. And then one more, the definition of work, of mechanical work, is just the force acting over distance. Okay. You probably picked that up in physics. And so the units of work have got to be equal to the units of force and then the units of distance. All right. So work has the same energy, or has the same units as energy, and so that's got to be equal to newtons times meters. And then you can break that down again into, using this up here. So you got kilograms, meters squared per second squared, which is, again, basically the same thing I wrote right there. But it's another way of writing it, because now I can from this I can pull immediately the relationship between newtons and energy. You know what I mean? So if I have newtons times a meter gives me energy, units of energy, and being familiar with this sort of thing can be helpful in keeping you from having to memorize these quantities. So one important quantity that you're probably not familiar with, but is going to be very important here. I mean, you're familiar with it, but probably not to the degree that you're going to need to be in this class. So there's the quantity of density, and this is my Greek letter rho. That's what it looks like. So the density is given by the Greek letter rho, and the units of density are the units of mass divided by volume, where this capital V with a line going through it is my symbol for volume. Okay, and so I can break this down. So it'd be kilograms and then meters to the -3. The units of volume are just cubic meters, right? So if I'm divided by volume, I get meters cubed. And then there's this concept of a mass flow rate. These are going to be important to you. So, and this relationship is going to be, it's going to come up in pretty much every section of this course. And then mass flow rate is given by this mass with a dot. Okay, and then the units of mass flow rate are the units of mass over the units of time, or the units of mass over time, which is just going to be kilograms, okay, times seconds to the -1. And so there's going to be a need to convert between volume flow rate, a quantity called volume flow rate, and mass flow rate. And so just by looking at it, you can see that the units of volume flow rate are going to be things like it's going to be like meters cubed per second. Okay, so how do I get from kilograms per second to meters cubed per second? I need a quantity that takes both kilograms and meters cubed. All right, I need a way of converting between kilograms and meters cubed, and so that's what density does. So just based off of the the dimensional arguments here, I can sort of derive that the mass flow rate is going to be at least proportional to, but in this case, it's exactly equal to the density times volume flow rate. All right, and this is going to be very important. You're going to have to be able to convert between units of cubic meters per second and kilograms per second over and over and over again. That's going to be a common trend. So it's going to be important that you at least you can commit this to memory or however you want to do it, but you're going to have to be able to convert between meters cubed per second and kilograms per second, or mass flow rate and volume flow rate. All right, so that's the basics for units, but an important aspect of it is that units used in an equation or units used in a formula have to be homogeneous, or formulas have to be dimensionally homogeneous. All right, and what that means is that all terms in the equation have to agree in as far as units are concerned. Okay, so here's a valid expression. You may recognize this as the Bernoulli equation. Maybe you've seen it in, or at least one form of the Bernoulli equation. You probably saw something like it in physics. Okay, and so I'm telling you this is a valid expression, and therefore you should immediately understand that all of these terms in the expression have to have similar units. All right, so we're just going to go unit by term, evaluate its units, and show that it is in fact dimensionally homogeneous. All right, so I got pressure divided by density. So this is going to be equal to the units of pressure times the units of density to the -1, right? So the units of pressure are going to be pascals, or and the units of density are going to be, oops. So I have units of pressure, pascals, units of density raised to the -1 is going to be meters cubed per kilogram. Okay. And now, if you remember from just a second ago, pascals can be broken down into this, or can be decomposed into the base units in this way. So that's pascals. Then I just have meters and kilograms are already in base units, so I got meters cubed and kilograms to the -1. All right, so the kilograms cancel. I got meters raised to the third power, and then again meters raised to the -1st power. So I get meters squared over seconds squared. Okay, so this term P over rho, pressure divided by density, has units of meters squared over seconds squared, which if you kind of look at it is just joules without the kilograms. So it's kind of an energy per unit mass is what this works out to be. All right, and so I could also write this as joules per kilogram. All right, now so let's look at the second term here. We got the units of v squared over 2. All right. The units of v squared, and then multiplied by the units of 1/2. All right. So that's going to be v squared meters squared per second squared. All right. And then the units of 1/2 are, it's a unitless quantity. Okay, so it's just a number. It has no units associated with it. All right, so that's what that little dash is supposed to mean. But essentially, I have meters squared per second squared, which again, I could also think of as a unit of energy per unit mass. Okay, and then likewise for GZ, I have G is the gravitational acceleration, and so that's got to be the units of gravity, or gravitational acceleration, times the units of z, which in this case is just the z coordinate, or so this is going to have units of length. So this is acceleration, which is meters per second squared, and then units of length, just another meter. And so I got meters squared per second squared, again, units of energy per unit mass. And so this constant, this c, is you don't know much about it, but you do know that its units must be energy per unit mass, or speed squared, or however the best way to interpret this is. In this context, it makes sense to interpret this as energy per unit mass. So what Bernoulli equation is actually saying is that these different forms of energy, I have energy associated with the pressure, energy associated with the kinetic energy, with the velocity, and energy associated with its position, the potential energy. If I sum up these three forms of energy and divide by the mass, I get a constant. Okay? So this is really just a rephrasing of the conservation of energy, and we'll get into that. Now, the last thing I want to cover is that there are some formulas or some terms in a formula some terms require that their arguments be dimensionless. Okay, so if you ever have like a sign, if the sign of a function or the sign of an argument shows up in an expression like this, the units must cancel. All right, so we'll have something like with t over tau. It's sometimes that, like, if you're dealing with, say, the voltage is a function of time in some oscillating electric circuit or something like that, or some oscillating system, like if you have a pendulum, this could show up, but the argument must be unitless. So the units of t must equal the units of this property, or this variable tau, so that when you divide them, the units of t over tau are, are unitless. T over tau must be unitless. Okay. Likewise for things like the exponential function. The exponential function, if you're not aware, is just e raised to the power of x over L in this case, where the units of x must equal the units of L, and so that the units of x over L are just, so the x over L is unitless. It just equals 1. So the units of x over L equals 1. X over L doesn't equal 1. The units of x over L equal 1. Okay? And then there's other things like the log. Maybe the log of something like v squared. I'm just making some of this stuff up. And so these units have to cancel, and we just showed that they did, right? So the units of velocity squared gives you meters squared per second squared, and the units of gz, which is in the denominator, gives you the same. So this is a valid, useful. This is a valid term. This could be a valid term in an expression.